In this lecture, we are going to look at the Knoevenagel reaction or the Knoevenagel reaction. The pronunciation actually sounds strange, but it's a very simple reaction. Now, the Knoevenagel reaction is addition of compounds with active methylene group to a carbonyl functional group of aldehyde or ketone. Now, everything still follows the same procedures that we'll be talking about since on addition of a nucleophile to a carbonyl compound. Now, the active methylene group, what are they? That is a question that you should ask yourself. Now, an active methylene group is a methylene group that has an electron withdrawing group, 2 electron withdrawing group about it. For instance, if you have, let's say, CH2, there you have this COOH and then this COOH. This is an active methylene group. Normally, a methylene group is this. Any group that has CH2, then with the 2 other bonds are regarded as what? A methylene group. Are you getting it now? So a methylene group is said to be active when it has 2 electron withdrawing groups about it. For instance, the carbonyl group is electron withdrawing. Are you getting it? I mean, the carboxylic acid group is electron withdrawing. And also, this group here is also electron withdrawing. This is carboxylic. So that makes this methylene group to be what? Active. Are we getting it now? Now, the active methylene group can be converted to a nucleophile by reacting it with a weak base, such as the amine. Now, the weak base we are going to use in this case is pyridine. So when you react the active methylene group with a weak base such as pyridine, it forms a nucleophile which can attack a carbonyl group. Now, what is the structure of pyridine? Now, that is not in the material, but you just have to know it. The structure of pyridine is a base, an amine, secondary amine. Now, this is the structure of pyridine with hydrogen here. Now, that tells us that pyridine has 2 lone pairs of electron. Now, those 2 lone pairs of electron can easily come abstract a proton from hydrogen. True or false? It's true. So, if it abstracts a proton from hydrogen, normally, let me write this in a way that the orientation will be suitable, right? So, something like this. We have CH2, right? And there you have COOH, and there you have COOH. This compound is active methylene group. Are you getting it now? Remove this and then put hydrogen here. You know why I did it like this? So that the lone pair of the amine can easily attack this and withdraw hydrogen from here. Okay, so when this attacks this, what will happen? What do you think will happen? It will abstract a proton from hydrogen, and then this bond here kicks in to form a negative charge. So the product of this reaction will be something like this. You have COOH, and then you have CH negative, because this one has been added, or you can decide to put the hydrogen here so that the negative will be on top of the carbon properly. Then you now have COOH. Are you getting it now? Now, this is a perfect nucleophile. This is a perfect nucleophile. This is a what? A perfect nucleophile. Are you getting it now? So this nucleophile now can easily react. The nucleophile can easily react with a carbonyl group to form a compound. Now, it said the use of a weak acid, this amine is found adequate. Forget about those. But just note that this can actually attack this, and this comes here, and then this forms a nucleophile. So how about if we use this now to attack a carbonyl group, like the one that is given? If you have something like this, let's say you have a group like this. What is this? This thiophene, okay? Thiophene carbaldehyde. You have C, and make it easier. So you have something like this. You have C double bond O, and then H plus this group, which is that's the lone pair of electron here, and then the electron group or the bond there. Then you have COOH. Now every one of us agree with me that this is a nucleophile, and then this is a carbonyl group. Okay, now this carbonyl group, this is a carbonyl carbon. This nucleophile can easily attack here. That's why we said it's known as the Knoevenagel reaction, in which an active methylene group, the active methylene group, is just acting as a nucleophile. It's called a nucleophilic addition reaction. Now, most of the reactions that we've been talking about is still nucleophilic addition reactions. Okay, so when this one attacks here, what do you think is going to form? This one here will come up here to form a negative charge. So the product of this reaction will be something like this. Okay, then you are going to have the thiophene, okay, this and this, and then you are going to have C. You know, this one attacks here. Let me erase this to form what? O negative, right? Then here will be what? Hydrogen. Then here will be C, and then here will be what? The COOH, and here will be COOH. Okay, now at this point in time, what do you think can be done, or what do you think will be done? Now the first thing is that a proton will be abstracted. Are you getting what I'm saying? A proton can be abstracted. That means you can hydrate it, or acid hydrolysis, in such a way that this hydrogen will be added here. So if you pass this through H+, which is hydrolysis, what happens? This one picks, not hydrolysis. This one picks up the proton from here. It can be protonated, rather. Let me use that English. It can be protonated. So when this negative charge attacks here, it becomes protonated. And then we are going to form something like this. Let me erase this so that I can write this here, because this reaction, I just gave it one page. So when this compound now is protonated, I'm supposed to use a red pen to draw this. So when this is protonated, what do you think is going to form? It's going to form an alcohol. Okay, so when it forms an alcohol, what you are going to have is something like this. This coming here, and then you form this, and then you have sulfur, this, and then you are going to form C. Here will be what? OH, and then here is what? Hydrogen. Here is carbon. Here is OOH, and here is what? COOH. Is that not so? Of course, we know we are left with one hydrogen here. There's supposed to be one hydrogen here. Supposed to be one hydrogen here. Let's not forget that. Okay, so that is the product of the reaction. Now, this product is not enough for us to just write this product. This product can undergo elimination reaction, whereby water is being eliminated. Are you getting it now? So if you remove water, you now say minus water. If you remove water from this equation, what do you think you are going to form? Now, where do you remove the water? You know there's hydrogen here. Let me make it a very easier for us. Now, you know there's hydrogen here, and there's OH here. Now, if you remove hydrogen from here, remove OH from here, what do you think we are going to get? Let's do something quickly. Remove hydrogen from here, and then remove OH from here. What do you think we are going to form? Removing hydrogen from here and OH from here will form a double bond here. Are you getting it now? So this will give us the final product, which is this, and then this, and then this, and then we have C, and then this is going to give us a double bond, because we know we have the hydrogen here, and then we have C, and then we have COOH, and then we have COOH. So you see how easy it is. Now, but this reaction was modified, right? This reaction was modified to give what we call the Dobner reaction, or the Dobner reaction. Now let's see how the Dobner reaction is. So erase us thing. Now this is a phenyl ring. If you have this as a phenyl ring, and then you have this phenyl ring is linked to a carbon, right? Now, if this carbon is linked to oxygen, and then you have hydrogen here, this is a carbonyl group plus an active methylene group, right? An active methylene group. Now, according to what we said, now in this case, they use pyridine as the base, and also piperidine also. They are almost the same, but just some differences in double bond and the rest. This piperidine. Okay, now at the end of the day, normally by the Knoevenagel reaction, what are we expecting from this reaction? By the Knoevenagel reaction, what are we expecting from here? Normally, by that reaction, we are supposed to get something like this. You know, this will be C, and here will be the phenyl group. Normally, if you practice the Knoevenagel reaction, you have this OH, Abi, and then you have H, and then you have C, and then you have H, then COO, H, and then COO, H. This is the Knoevenagel reaction. That is what we get as our product if we follow the Knoevenagel reaction normally. Before it was dehydrated. Are you getting it now? But in this case, what they did was it was dehydrated and then decarboxylated. Are you getting it? So if first of all we dehydrate this, what do you think is going to form? Dehydration means removal of what? Water. So if I dehydrate this, I mean I'm removing OH from here and then removing hydrogen from here, right? So what am I going to form at the end of the day? It's going to give me pH and then C and then double bond and then carbon and then hydrogen here, right? And then I'm going to form COOH and then COOH. Now, if I remove this removal of what? Water, H2O. Now, as it is now, if I should remove carbon dioxide, which is CO2, that means decarboxylation. That's what this is called in organic chemistry. Why this is what? Dehydration. So what do you think this is going to form? If I decarboxylate this, what do you think I'm going to form here? Now, this is going to give me, normally, there is, there ought not to be a double, okay? There's a double bond here. Okay? So if I decarboxylate this, remove COOH from here, I mean COO from here, what am I going to form? This hydrogen comes here, and then the product of the reaction will be P. This phenyl ring, note that we cannot keep writing phenyl all the time. What we remove was COO2. The hydrogen is attached here, and then you have COOH. This product is called cinnamic acid. It's called what? Cinnamic acid. So that is for the Knoevenagel reaction. It's a reaction whereby an active methylene group add nucleophilically to a carbonyl compound to give the product. Now the product can be dehydrated to give another product. Okay, now it can be remodified using the reaction called the Dobner's reaction, whereby after dehydration you decarboxylate again. So the Dobner's reaction is just like a continuation of the Knoevenagel or Knoevenagel reaction. Are you getting it? It's just like a continuation of the Knoevenagel reaction. All you just need to do from the after you must have gotten the product of the Knoevenagel reaction is to decarboxylate it, and whatever you get gives you the product of that reaction. So that is that for this quest. Thank you very much for your time. Like we said, this is a phenyl ring. This pH you see here is a phenyl ring. Phenyl is something like this. We cannot continue drawing this. That is why we decided not to place it into this equation. Okay? So you can always represent it with this. At the end of the day, if I come here, I can decide to remove this and then put the phenyl bond, which is something like this. Right? Then put this, and this. Because that is phenyl. This is what is called the cinnamic acid. Okay, this is what is called the cinnamic acid. So the Dobner's reaction can be used for the synthesis of cinnamic acid. All right, so that is that for this quiz. Thank you very much for your time.